We now move on to example 2, part B. We're solving linear systems by the substitution method. We have a system of equations where x and y are on the same side of each equation, but it's rather easy to solve for y in the first equation. So when you have a situation like this, you can often use substitution fairly easily. So what we might do there is subtract 5x from both sides. Let's write minus y equals minus 5x plus 5. And then if we multiply both sides by -1, that can be rewritten as y equals 5x minus 5. Now what we'll do at this point is we'll take 5x minus 5, and in the second equation, in the other equation, make sure you don't plug back into the equation you were just working with. Into the second equation, replace y with 5x minus 5. So that's the substitution step. 3x plus 2, and then for y we write 5x minus 5 equals -10, and then solve for x. 3x plus 10x minus 10 equals -10. 3x plus 10x is 13x. Adding 10 to both sides, we get 0 on the right. If we divide both sides by 13, we get x equals 0 over 13, but that's just equal to 0. So the x-coordinate of our solution is 0. So what is the y-coordinate? Well, let's just use this version of the first equation where we solved it for y, and then we can easily determine the y-coordinate. So y would be 5 times 0 minus 5. That is 0 minus 5, which is -5. So here again, this is a system of equations with just one solution. That solution would be 0, -5. Once again, we have a consistent system with independent equations. So sometimes in using the substitution method, we have to first solve one or the other equation for x or for y before we can actually apply the substitution step. I should just add, as long as that can be done fairly easily, substitution can be a good choice for that particular type of system. The second method of solving a linear system is the addition or elimination method. And this is a more generally useful method than substitution because you can use it for practically any system of equations, a linear system that is. So in particular, if x and y are aligned on the same side of the equal signs within the system, then the method can be used almost immediately, and a lot of times will yield a result more efficiently than the substitution method. So let's show how the addition or elimination method works. I'll just call it the addition method because what it involves is adding the two equations in such a way that you cancel out one of the two variables. So if we look at example 3a, 4x minus y equals 6, 3x minus 4y equals 11, we need to choose either x or y to be eliminated through addition. And if we note that if we multiplied the top equation by -4, then the y terms would be positive 4y and negative 4y. And if we added the left-hand sides and right-hand sides of the equations, then the y terms would cancel. It's easier here to eliminate y than it is to eliminate x because of the types of coefficients we're dealing with. That is the numbers in front of the variables. So we're going to eliminate y here. And so what we have to do with the first equation is multiply every term by -4. That's going to give us negative 16x plus 4y equals negative 24. And then the bottom equation doesn't need to be changed at all. So sometimes it's only necessary to change one of the two equations. Sometimes it's not necessary to change either equation. You can just add them immediately and either the x's or y's will cancel. But often you have to at least modify one of the two equations. If we now add the left-hand sides and right-hand sides by adding like terms, negative 16x plus 3x is negative 13x. The y terms are going to cancel as was intended. And then on the right-hand side, negative 24 plus 11 is also negative 13. If we divide both sides by negative 13, we obtain x equals 1. So now we have the x-coordinate of our solution. We still need the y-coordinate, of course. What we need to do then is just choose one of the two equations in our system, substitute in x equals 1, and then solve for y. Why don't we just use the first equation? And let's just use its original form, 4x minus y equals 6. So if I replace x with 1 and write the rest of the equation and solve for y, then I'll have my y-coordinate. 4 minus y equals 6, subtracting 4, minus y equals 2, dividing by negative 1, y equals negative 2. So here again, there's just one solution. That solution would be x equals 1, y equals negative 2 as an ordered pair. Let's now look at example 3b. And here we see that we have coefficients for x of 2 and 3, and for y 5 and negative 2. So the coefficients are not particularly compatible such that we could just change one of the equations easily and obtain opposite coefficients for either x or y. So I'm going to choose, you could eliminate either x or y in this example. Since we eliminated y in the previous example, I'm going to eliminate x in this example just to do it a little bit differently. And what we would notice is that with coefficients of 2 and 3, the least common multiple would be 6. So if I multiplied perhaps the first equation by 3 and the second equation by negative 2, then the coefficients of x would be 6 and negative 6 respectively, and then by adding the equations, the x terms would be eliminated. So if we multiply each term in the first equation by 3, we obtain 6x plus 15y equals negative 15. If we multiply each term in the second equation by negative 2, we obtain negative 6x plus 4y equals positive 34. Now if we add, the x terms will cancel. The y terms will add to 19y, and the right-hand side, negative 15 plus, let's see, right, so we have, yeah, I have this right. The right-hand side will also be 19. Then if we divide both sides by 19, we obtain, we obtain y equals 1. Now having having a little bit of trouble here, sorry about that. Having solved for y, if we now substitute back into one of the two equations, let's use the first equation, 2x plus 5y equals negative 5. We could use either equation. So we have 2x plus 5, but y now will be replaced with 1 equals negative 5, and that gives us 2x plus 5 equals negative 5. If we subtract 5 from both sides, that gives us 2x equals negative 10, and dividing both sides by 2, x equals negative 5. So here again, one solution. X is negative 5, y is 1. We write that as the ordered pair negative 5, 1. So in this example, we had to modify both equations. Occasionally this is necessary. If the coefficients are such as 2, 3, 5, negative 2, where one coefficient is not a multiple of the other, then we have to multiply both coefficients by something to obtain whatever the least common multiple is for those coefficients. So that's going to require you to change both equations. Otherwise, the method follows just as it did in the previous example. Thus far, all of our systems have had exactly one solution. They've been consistent systems with one solution. What happens if we encounter a system that has no solution, that is inconsistent, or has an infinite number of solutions, that is, it's dependent? If a linear system is inconsistent, we will obtain a contradiction, such as 0 equals 2, when we attempt to solve the system by substitution or addition. So anytime you obtain a contradiction, 0 equals 2 or something similar, then regardless of whether you're using substitution or addition, that indicates that the system has no solution. It's inconsistent. In such a case, we can denote the solution set as the empty set, using the empty set symbol, which is a circle with a line slash through it. If the system is dependent, that is, if it has an infinite number of solutions, we will obtain an identity, such as 0 equals 0, or 5 equals 5, or something along those lines. And we can represent the infinite solution set in terms of one variable. I'll demonstrate that so you'll understand what that means when we look at our second example. So example 4 says, identify the system as inconsistent or dependent. If dependent, express the solution set in terms of one variable. Let's look at example 4. We have y equal to negative 2x plus 1, and 2x plus y equals 6. This is set up well for substitution. If I replace y in the second equation with negative 2x plus 1 from the first equation, I'll obtain 2x plus, then replace y with negative 2x plus 1 equals 6. That is 2x plus negative 2x plus 1 equals 6. The left-hand side simplifies simply to 1 because the 2x and the minus 2x cancel. So we obtain 1 equals 6. Well, this is an example of a contradiction. If we obtain a contradiction, it indicates that the system has no solution. That is, it's inconsistent. And has an empty solution set. So for an inconsistent system, we can describe the solution set with the empty set symbol. So this is what you might see if you're solving a system of equations and the system has no solution. We'll continue with part B of example 4 in the next video.